I'm Mengkun from Stony Brook University. I also hold a joint position at BNL. So today, I'm happy to talk about Landau-phonon polaritons in Dirac heterostructures. I also want to thank the organizers for this nice event. This is the biggest double rainbow. Of course, when you see fringes, you get excited. At this scale, it's fabulous. Of course, this is very hard to see from this low signal-to-noise emitter. But as a scanning probe person and an imaging person, I did a bit post-processing to this image so that you can see this gradient magnitude a little bit more clear. If you still cannot see it, of course, the dashed line always help. And this distance between this double rainbow actually is not a polariton wavelength or half of the wavelength. It's actually called Alexander dark band. Okay, and it basically is a photonic gap in the universal scale that formed by the liquid, small liquid drops. Okay, great. So today I will have a very brief discussion of what we can do. We basically have a new type of experimental tools. We call it coil magneto-snom, which is a which is a snom that can operate at 5 Kelvin and 7 Tesla magnetic. And we use this so-called Landau level nanoscopy to study many-body physics in 2D electron materials. And if time allows, I doubt it because I made this rainbow joke. So I will discuss using polariton cavities to study correlated electron materials as a sensing platform. Okay? So this is a joint collaboration between multiple groups. So Stony Brook is in Long Island, and which is very close to Columbia University and BNL. So this work is particularly done first by Michael, which is a master student with me, now a PhD student with Dmitry Basov. And Lucas Wiermir is a postdoc with Larry Carr at BNL and also with me. And we also have a lot of theoretical effort from Misha Fogler and have very nice discussions with Alexei Kuzmenko. So, of course, electromagnetic nanoscopy is no stranger to many of you, right? So at microwave frequency range, Fritz Kelman actually did many years ago that you can actually do a scanning probe at the microwave frequencies within magnetic field. He saw quantum oscillations within magnetic field up to several Tesla with microwave imaging, right? And if you are in the field of MEME, so-called microwave impedance microscopy, they have achieved that many years ago, that you can do regular scanning probe even in a dilution fridge. For example, Kerji Last group and Modica and Allen's group at UC San Diego, they demonstrate you can do this at very low temperature and up to 9 Tesla or even 12 Tesla nowadays, right? Of course, this is at microwave frequency range. Basically, all you need is a coaxial cable that guides your microwave into the cryostat. I will argue that at visible infrared or terahertz frequency range, this is much more challenging, right? Because, for example, proposed by Marcus many years ago, he demonstrated that you can do this at a cryogen temperature, but we have a very bulky optical detection system, and you have to put a parabolic mirror inside of the chamber so that you can focus light and gather scatter light inside of the chamber, which you have to have a very high NA objective, right? Of course, this is, I said bulky, not for his system, but all the system is kind of bulky compared to other AFM type of system. So this is another example from Jigang Wang's group at Ohio State University. They managed to do this also with 5 Tesla magnetic field and with terahertz snom, right? So he also used a wet system, that is, you have to use liquid helium. So we actually come with a very different approach. As you know, liquid helium is expensive, and graduate students are even more expensive these days, at least in US. So we want to build everything in a closed cycle cryostat so that you can you don't have to deal with the liquid helium and have time to do the recycling. So we basically put our AFM stack inside this, by the way, this is all the stacks are from AutoCube, and the controller's program is also from AutoCube. So we have a fixed tip and have an FM stick, and we have this off-axis parabolic mirror sitting on another positioners, so that you can focus light onto the tip, and the light is collimated from outside of the chamber, and through the side windows you can focus the light onto the tip. So this is very critical because you need very high NA objective for focusing and scattering light. And this magnetic field is 7 Tesla out of plane. Of course, we have other plans to do this in-plane geometry as well. Right now, our record is 5 Kelvin at sample temperature, 7 Tesla magnetic field. The Tesla noise at 10 Kelvin is below 1 nanometers. Considering this is a closed cycle system, I would say this is not bad. Of course, we are still improving the specs on this. We have 2 systems that is fully running, one at the infrared frequency and the other at the terahertz range. It's interchangeable, but basically you just have to change the windows. So it's very convenient. So this is one of the first images that we got recently at below 15 Kelvin mark. So this is at 12 Kelvin. What you see is basically polaritons on MO03, and this is at 7 Tesla magnetic field, right? So this is MO03 microcrystal, so you can see some polaritonic fringes. I will not discuss the detail because I think Siyuan Dai would like to publish this in another journal soon. We also can observe the plasmon polaritons in graphene, right? So you can see this, the image quality is quite good in general. Of course, you might ask, what's the magnetic field doing here? Not much in this case, but I'll show you what it can do in the other cases. We also see the second order polariton mode, which you cannot see on this screen, but I just plotted here. So over this 10, 20 micron length scale, you can still see 100 to 200 nanometer polariton waves at this low temperature and high magnetic field. So I would say this is quite nice. So we measure 3 things with our systems. Of course, topography, right? You have the FM, near field scattering signal, which you measure the optical properties by measuring the scattered signal. You can also put electrodes on it. If Frank Koppen was here yesterday, he would told you more about it. You can put electrodes on it and probe the so-called near field photocurrent, right? And this photocurrent will, basically the chip will locally enhance the field. And in graphene in particular, this enhanced field will give you a temperature gradient locally under the tip so that you can measure the photocurrent generated in near field, okay? So we measure these 3 things simultaneously with our system. So with magnetic field, we can basically characterize 4 length scales simultaneously, right? One is the polariton wavelength. The second one is the magnetic length. In terms of graphene, is 10 nanometers at 7 Tesla magnetic field. Of course, this magnetic length is smaller when you have higher magnetic field. You also you can detect hot carrier diffusion lengths through this photocurrent measurements and superlattice periodicities if you have more rays. And you can imagine all these 4 length scales, if they intervene with each other, you can have many interesting many-body physics, especially for charge-neutral systems. So polaritons, we have learned a great deal in the first case of polaritons. I characterize them in 3 different cases, not necessarily true, but this is how I characterize them. One is when B equals 0 and you have very large doping, so you have this plasma dispersion that you measure with, of course, near-spec system. So this, of course, Dimitri and Frank and Renner, they showed a lot of pioneer work on this. I think you all know. But basically, if you have no doping, then this plasma dispersion will be very flat, right? You won't be able to measure the plasma dispersion. So then we can go to the second case, which your doping is near 0, so that you are in the charge neutral point, so that you can access actually many-body effects in graphene. But now with applying magnetic field, you can have these quantized Landau levels you can access due to the interband or intraband plasma or magneto-exciton excitation, I call it. And you can have 0 to 1 Landau transitions, -1 to 1, -1 to 2, -2 to 3, -2 to 2, so on and so forth. And these Landau levels will scale with the magnetic field, right? This is a nice polariton that you can tune all the way from terahertz to infrared to visible by magnetic field, which is great. Of course, there's a case 3, which you have both large doping and large magnetic field, and you expect to have some unidirectional chiral edge mode that is topological, that only propagate in one direction in your low-dimensional materials. We will not discuss the case 1 and case 2 in this talk. We will just focus on this one. Okay? So I will show you in the first case, the first topic, I will show you just 0 to 1 Landau transition. I will show you just using Landau level spectroscopy, we can do imaging of these Landau transitions in real space with 10 nanometer resolution. And in the second case, I will probe all these other transitions up to 4 or 5 different Landau levels using so-called polariton enhanced imaging. So you can hybridize these Landau levels, which is highly tunable, again, with magnetic field, to hybridize it with the phonon polariton modes at this frequency range, right? So we can do this because we can freely tune our polariton frequencies, these magneto-polaritons, to match the phonon polaritons in HBM. Okay. So this is at 0 Tesla. You have a graphene sandwich between HBM, and you have 2 electrodes on the side and 3 edges on the top and bottom. As you apply magnetic field, you can see that at certain magnetic field, the graphene suddenly becomes very bright. Okay, so you have a very nice on-resonance behavior between our infrared light and the graphene. So this is simply because that at low magnetic field, you have this universal optical conductivity, which is very low, so you do not see much at low magnetic field, right? This is basically no insulator, since this is a charge-neutral graphene. And as you apply magnetic field, you form these quantized Landau levels. And of course, at low magnetic field, your laser frequencies is not on resonance with these peaks, for example, 0 to 1 peak. But as you increase your magnetic field, these peaks actually shift to higher frequencies. And now at 6 Tesla, your peak actually now arrive at the laser frequency. So that you can actually see this is on resonance Landau level excitation, interband Landau level excitation in real space. And of course, we have electrodes on it, so we can measure the photocurrent, right? So again, this is photocurrent is measured by tapping this tip and detect the modulated photocurrent through these 2 electrodes. And you can see that at 0T, you have this photocurrent concentrated at 2 electrodes, which is understandable because at the 0 temperature, you will have so-called seabag effect. And this seabag effect is basically goes to arbitrary directions under the tip due to the heating. And at this middle part, you will have equivalent amount of current goes to the left and right so that you will not detect any photocurrent. As your tip is closer to 1 electrode, you can detect the photocurrent in one direction or the other. And in high magnetic field, you will induce photocurrent, but this photocurrent will rotate due to Lorentz force. You will rotate around the tip, right? Very naive, simple picture, so that you can now access this edge mode that is unidirectional. So on the top edge, your current is to the left. On the bottom edge, your current is to the right, or to the left, and to the right. It doesn't matter which direction. Of course, if you switch magnetic field, you will see this direction switches as well. There are some defects here that also you can see. There are some p-n junctions here. You can detection. You can also do this in photocurrent in the gate-dependent measurements. So you basically probably block the 0 to 1 transition by applying gate, right? So you can block away the transition and make this bright contrast go away. In the photocurrent, you can also gate it away so that you do not have these edge channels anymore. So this is nice, right? We can actually assess Landau level physics now in real space and see these edge channels that potentially can be topological in many different material systems. And you can see, even with this projector, you can see a bright edge here. So this is actually exciton magneto-polaritons. And in some samples, we see one. In some samples, we see two fringes. So that we can actually have a full map of the dispersion of these magnetoplasmons or magneto-exons within our sample. But I will not discuss that. I will instead discuss how we detect these other magneto-exon excitations with hybridization to HBN. So what we do is now we put a thicker HBN beneath the graphene, and now we can have polariton modes to access in the infrared frequency range. And this is just a typical dispersion of phonopolaritons in HBN at 0 magnetic field. We have the first branch and higher order branches, of course. So we are essentially detect only the first branch in here. So this is simulation and calculation, right? And in high magnetic field, at 3.3 Tesla, your -2 to 1 transition happens to interfere with this phonon polariton mode. So we can apply magnetic field so that this -2 to 1 transition actually intersects here. And this is actually a strong coupling because you see a mode gap actually in here. So this is, the red one is the magneto-exons that is tunable. The black one is just the original phonon polaritons. You can see a clear gap here. So in the experiments at 0T, we see that in graphene HBN, you can see this polariton is launched by this gold antenna, no problem. And in high magnetic field, of course, since you have a gap opening, so that you will see that this polariton mode is totally stopped at 3.35 Tesla magnetic field. Okay? So this is a highly tunable magnetic field tunable phonon polariton or hybridized polaritons that you can basically achieve at any frequency range, right? As long as you have phonon modes or other extonic mode or magnon modes there, you can tune your Landau polaritons to match the frequency, which is nice. And of course, you can do a line scan and at the same time change the magnetic field. This is the line scan at the edge of the gold. And as you change the magnetic field, you can actually see many different Landau levels, including the ones that we saw at 3.3 Tesla. There are actually many others. If you integrate it versus the distance, right, just show the magnetic field dependent near field signal, you can see many different orders of Landau level transitions. -1 to 2 is the largest one in this frequency range, and there are a few others. Now, the chair has stands up, so I have to rush a little bit, just show you the many-body physics through polariton couplings. Because, as you know, the Landau level spectroscopy is one very unique tool to study effective Fermi velocity in this kind of 2D electron systems, right? So we have photon energy in this equation. We have magnetic fields, so we can extract the magnetic length. We have the Landau indices, so that we have everything in this equation to work out the effective Fermi energy, right? As with the effective Fermi energy of graphene, you can actually work out two different kind of scenarios to change this effective Fermi energy. One is the renormalization, Fermi renormalization of the quasi-particle dispersion, so that you have a nonlinear kind of Dirac dispersion. And also you have this so-called magneto binding energies. Without going into the details, we show that these forbidden transitions, which is the red, actually give you higher exciton binding energies than those allowed transitions. The fact that we can detect the forbidden transitions is because that we are now at a non-zero momentum, right? At zero momentum, your -1 or the same indices transition is so-called optical. It's due to the selection rule, right? It's optically forbidden. But in our case, with near field, I argue that with finite momentum measurements, we access to all these modes, include the so-called allowed transitions and the forbidden transitions. I'll skip most of this. I will just give you a take-home message. So now we can control phonon polaritons and other types of polaritons with magnetic field using strong coupling and mode hybridization. We use infrared light to access forbidden transitions within the field, and we can study many-body physics using Landau level nanoscopy with 10 nanometer resolution. I think I'm almost on time, so I will skip some of this future work. We can do, for example, Hofstadter butterfly with nanoscale using photocurrent nanoscopy. We can basically study cavity-enhanced QED. This paper describes theoretically what we have just done with graphene HBN system, and they predict ultra-strong coupling, but we saw strong coupling, but in the future we can also do this. We can also measure other kind of phase transition materials with this system, of course. And with that, in the last slide, I just want to do a little bit advertisement because we work very closely with Larry Carr and Lucas at BNL. So we have now infrared near-field nanoscopy instrument at NSLS2 at BNL. We have a very broad spectral range, very similar to what they can do in LS, advanced light source at LS these days. We have a very broad spectral range of 5 Tesla to all the way to 180 Tesla. And this is nanoscopy, okay? So if you have proposals, please submit before September 30th, and if you want to talk to us, you're more than welcome. And I will just put the slides here. I want to thank my group members and all the funding agencies. Thank you.
We have time for 1 or 2 questions. From the back.
Thank you, Mengkun, for the nice talk. Can you change the population in the different Landau levels to control kind of which transition are more or less important?
So you are saying control the backgate, or?
Yes.
Yes, yes. So I think I showed one. I know I flushed through many things. But I showed one.
No, I mean here, if you would have a backgate dependence here, can you make different levels more or less prominent?
Yes. Yeah.
Okay.
Yeah. So you can shift. Of course, you can probably block one by one of these Landau levels, and you can see how it changes with. So we can actually do quantum oscillations now at 5 Kelvin. So we can see real space image at gate-dependent quantum oscillations, and see the edge state and also the bulk state as well.
Really
so,
cool.
Yeah,
Thank you.
that's very good suggestion.